chemical delay. So there we discuss various sub-processes that happen during physical and chemical delay, which involve forming ignitable mixture and forming radical from a stable molecular structure. Fuel has a significant role to play, as we have discussed, in each of the processes that happens during the physical delay as well as the chemical delay time. So to summarize it, the major influencing role of fuel in CI engine combustion, CI is compression ignited engine combustion, is that it influences start of combustion. As you know, once the start of combustion is influenced, the subsequent combustion phasing and everything will get modified. Accordingly, the engine performance and pollutant emissions are going to be different. So fuel has an important role to play in influencing the delay time, ignition delay time in a CI engine. In a SI engine, spark ignited engine, fuel has a major influencing role of knocking or abnormal combustion. There, the requirement of fuel are totally different from what we have seen in CI engine. In spark ignited engine, as we know, the flame that we produce by discharging high voltage electric spark has to move across the combustion chamber and it has to ignite the fuel air mixture. The fuel air mixture at any point of time should not self-ignite. So the role of fuel here is the fuel should resist self-ignition. It should not self-ignite. Otherwise, it leads to abnormal or knocking combustion that will eventually damage the engine. We don't want that to happen. So fuel role there is to resist ignition, self-ignition, meaning that it should possess a better antenna quality measured in terms of octane number. So we discussion that the ignition quality requirements for CI and SI engine applications are just opposite. For CI engine application, we want a fuel with better ignition quality. For SI engine application, we want fuel to resist ignition, meaning we want fuel with a poor ignition quality, measured in terms of octane number. In a CI engine, it's measured in terms of cetane number. Okay, so after that, we are moving into the second topic. Here, we are going to discuss about what criteria. We have understood the major influencing role of fuel in engine combustion, SI and CI. And now we are moving to the next topic, which is about the criteria that we use to select fuel for SI and CI engine application. Fuel, as you know, it's energy source. The combustion reaction, exothermic reaction, produces thermal energy, which is what we are converting into mechanical work in IC engine, and engine is the energy conversion device. It converts thermal energy into mechanical work. So fuel is a source, energy source. Now we are looking at the broader picture here in terms of consumption of energy. So we have limited energy resources in the globe, across the globe, and it's being shared across different sectors. Transport sector is the second largest consumer of energy that is available in the globe. 20% of the total available energy is being consumed by the transport sector, which is the second major consumer of energy, available energy. Which sector is the primary consumer of energy?
Power sector.
Power sector. Exactly. So power sector is the primary consumer of energy available in the globe. Okay. And transport sector is the second largest consumer of energy. With current consumption level is 20%, and it is predicted that it is going to get doubled to 40% in another 20 years, 2040. The predictions are the energy available globally will be consumed by around 40% by the transport sector. You could see a tremendous increase, right? It's almost double. So this is primarily because the requirement, energy requirement for transport sector is going to shoot up. That is what the predictions say. This is understandable because the consumption of energy is going to increase. It's not going to drop. Primarily because we need energy. We need this sector, transport sector, right, for economic progress of any country. Especially the developing nations are going to consume more, like India. The developing nations are going to consume more energy in the upcoming future. So that's why the prediction shows that it's going to get double. And out of this total energy that is consumed by the transport sector, if you look at this pie chart, so I have given the distribution of energy consumed or the energy that is met in the transport sector with a different fuel. So what you could see here is petroleum. Petroleum is crude oil. the fuel that is produced from petroleum meet 95% of the demand of the transport sector. The fuel that is biofuel, which is produced from renewable sources. Biofuel here primarily mean biodiesel and ethanol. In some other countries, ethanol is used along with gasoline. In India also, the mandate is going to come. They plan to include up to 20% ethanol along with gasoline. Currently, 10% ethanol is included along with gasoline in countries like US. If you go to any pumping station, it's 90% gasoline, 10% ethanol. So biofuel share currently is 4%. Petroleum, that is fuel produced from crude oil, is 95%, and the rest 1% is met with gaseous fuel, LPG and CNG. This is liquefied petroleum gas, and this is compressed natural gas. Its share is only 1%. 99% of the demand, energy demand, or the fuel demand for the transport sector is met with liquid fuel. 1% is with gaseous fuel. This is a status of the demand, how it is met with different fuels. Okay. So the takeaway here is liquid fuels are the primarily used in the transport sector. The fuel demand for the transport sector is met primarily with liquid fuel. Okay, so we know that the fuel exists in all three states of matter: solid, liquid, and gaseous. Okay, solid fuels cannot be used in IC engine, so this is ruled out. We have not designed IC engine to handle solid fuel like coal. Okay, and this solid fuels are primarily used in power generation, especially in India. Coal is the primary source, energy source for producing electric power. We have a lot of thermal power plant. They use coal as a source, energy source. For the transport sector, IC engine application, we have two options. One is liquid fuel produced, liquid fuels. And then second one is gaseous fuel. You have two options. Out of these two options, the surprising thing is 99% of the demand, fuel demand for the transport sector is met with only liquid fuel. Only 1% is gaseous fuel. Okay, out of this 99%, 95% is from crude oil. That is from gasoline for SI engine. I mean, you are processing crude oil to get gasoline or petrol, which is used as a fuel in spark ignited engine. Diesel is a fuel used in compression ignited engine. 95% of the demand, total demand, is met only with these two fuel. And this is happening right for almost 100 years now. We could not find any suitable replacement for this two fuel for SI and CI engine. It's surprising thing because these two fuels possess some distinct features which makes them unreplaceable by any other alternative options. Okay, the other important reason is the infrastructure currently we have has been built over a period of time. Okay, there is a huge money, huge investment and time that is being spent to build the current infrastructure to fuel our ICE powered vehicles with gasoline and diesel. So it's mostly these two fuel that we use, and 4%, as I said, is biofuel, primarily biodiesel and ethanol. And gaseous fuels there are a lot of options in gaseous fuel. Currently, these two fuels are mostly used. One is LPG, other one is CNG. You would have seen in some other light segments, light motor segments like auto rickshaws and even medium segment, right? Passenger car, auto rickshaws. Some of the buses also run with the gaseous fuel in a dual fuel mode. Okay, so LPG, you know, it's primarily used for domestic cooking purpose in India. It's liquefied petroleum gas. It consists of two components. One is propane. The other one is butane. So it consists of two components, propane and butane. And the typical share is 40% and 60%. This proportion is going to be different in different countries. In India, the LPG that we use has 60% butane, 40% propane. Okay. So this is what is liquefied petroleum gas, and CNG, compressed natural gas. It's primarily methane. 90% is methane. That is what is natural gas. It's a naturally occurring fuel source. Okay. So it's a natural gas methane. That is what is CNG. Now, the question to you is, why can't we increase this share, gaseous fuel share? What problem that is encountered if we use gaseous fuel as a source for powering our IC engine? Why do we rely heavily on liquid fuel?
Handling and transportation, sir. The storage space in the vehicle is increasing.
Storage space in the vehicle is going to be increased. Why is that?
The space taken by gaseous gas is going to be higher than liquid, and liquid will be higher than solid.
The space taken by gas.
Sir, generally, sir, these gases are stored at higher pressure up to 400 bar. So it is very difficult to bottle it and then transport it, and that all those infrastructure become costly, sir. That's what we understand.
Why we have to compress? Why we have to compress gaseous fuel for IC applications?
Because again we have to convert it into
Sir,
as far as I can understand, it should be somewhat in a vaporized form.
Sir, actually, we don't have to keep LNG or LPG in gaseous state. It can be stored in liquefied state itself, same like how it is happening for these auto rickshaws, what we have now, sir.
Yeah.
So, so the storage actually should not be an issue, sir, as far as I can say.
Storage is not a problem.
Yes, sir, because the expansion ratio will be higher when it changes from liquid to gaseous state.
So you are saying that storage is not a problem with the gaseous fuel?
Should not be, sir.
But what I am trying to highlight here is, if it is not a problem, we should scale it up, right? We have only 1% SAR from the gaseous fuel. So it means there is some inherent problem with gaseous fuel.
So what
Yeah, also you said it exists in the liquid phase, right? But under ambient pressure condition, it exists in the gas phase. You have to pressurize it to liquefy.
Yes, sir, correct, sir. Yes, sir.
So handling
So
is
anyway, you have to
difficult.
pressurize it. Anyway, you have to compress it. Okay, even including LPG.
Yes.
Yes, sir.
The problem, the primary problem with gaseous fuel is there is something called volumetric energy density.
exactly?
What is volumetric energy density?
Sir, what I understood about this thing is, like, suppose we have a 100cc engine for time being. Just I'm telling you, sir. So suppose with the gaseous fuel, the total volume, suppose in one stroke we are getting some X amount of air in the chamber. Now, if we have this gaseous fuel, then what will happen is it will occupy some. What I mean to say is the volume of air that is being there over there. So effectively, the total volume, the total mixture present in the 100cc engine with respect to gasoline or diesel, it will be lesser effectively. So suppose if the engine were working with the 100cc capacity with the CI or SI engine, with the gaseous fuel, it will be probably 95 or 90, 97 or 98 or something like that, 90 in that way. So the total output of the engine of 100cc engine for the gases, what I mean to say is, for the gasoline or CI engine, it will be better compared to a gaseous fuel. That is my understanding, sir.
Okay, so coming back to what I said, volumetric energy density is the energy contained in the fuel per unit volume, right? That is measured in terms of megajoule per meter cube or megajoule per liter. So in the previous class, I said that we are storing fuel on volume basis in IC engines. We are metering fuel on volume basis. Our fuel injection system meters fuel on volume basis. So everything is on volume basis, right? We store fuel on volume basis and we meter fuel in the injection system on volume basis. It's never on mass basis. Okay. Because of this, I have a problem with gaseous fuel. Its volumetric energy density is going to be very, very low. Its gravimetric energy density is high. Gravimetric is mass basis. But on volume basis, the energy contained in a gaseous fuel is very low. Very low. Okay, so megajoule per meter cube or megajoule per liter, it's very low. Because of this, I need to store more fuel. Okay, so the fuel tank capacity is going to get increased. So we have a compact system, vehicle system. Any automotive or propulsion system is known for its compactness. So typical fuel tank size for a motorcycle is around 5 liter. For a passenger car, it's 30 to 40 liter, right? That is enough. So when we travel for a long distance, we no need to refuel it often if I have a high volumetric energy density fuel. But if I have a gaseous fuel, I have to store larger volume for a given distance that is covered. So I have to increase the storage capacity, space that is required to store such a large volume of fuel is going to scale it up, right? So it's almost like an impossible task that I can, otherwise I have to refuel it often, refuel the vehicle often when I take a vehicle for a long drive. So this is a problem. So to avoid that, what we do is we compress. This volumetric energy density of gaseous fuel can be increased if I compress fuel, right? So we need to compress the gaseous fuel, without which we cannot use it for IC application. If you take, for example, hydrogen as a fuel that we want to use in IC engines, we have to compress it typically to a pressure of 700 to 800 bar. If I want similar volumetric energy density as a liquid fuel like gasoline or diesel, if it is compressed natural gas, I have to compress it to a pressure value of 200 to 300 bar. This is a typical number I am giving to get a comparable volumetric energy density as a liquid fuel. Right, so gaseous fuel, the problem is it occupies more space and poor volumetric energy density because of that. So I can increase volumetric energy density, make my system compact by compressing it. So, but I need to compress it to such a higher pressure value for a comparable volumetric energy density as liquid fuel. Now I have a problem here. There are two things here. One, there is the energy and cost involved to compress the fuel to such a higher value. The other more severe problem I will get, for example, if you take the case of hydrogen. If I compress hydrogen to a pressure of 700 to 800 bar, what problem we will encounter?
Safety issues. Safety issues.
Safety issues. So what kind of safety issues?
Leakage.
Suppose I travel in the
leakage
passenger car with hydrogen as a fuel. I have compressed it to this pressure level and store it in the tank, okay, to such a higher pressure. What typical safety issues I will encounter?
Easily explosion. Chances of leakage and explosion.
Leakage and expose. Leakage. So hydrogen, you know, it's the lightest gas. Storing hydrogen, so you have a lightest gas that's being compressed to a higher value of 800 bar. Now designing a fuel storage system, leak-proof fuel storage system is a challenge with the hydrogen kind of fuel because it's prone to leak. Because it's lightest, right? It's prone to leak. So you have to provide a leak-proof system for a lightest gas at such a higher pressure. It's a challenge, design challenge. Okay, so you have to store it in such a way that there is no leakage. The problem, other problem with hydrogen is you have to carefully choose a material because hydrogen can diffuse into metallic structure. Once it diffuses into metallic structure, it will make the metal brittle. What will happen if the metal becomes brittle?
It will break very
It will explode and because of higher pressure, it will explode.
Break into pieces.
Yeah, once a material loses ductility, once it becomes brittle, it is prone to crack. Once it cracks, it leaks. Okay, so hydrogen diffuse into metallic structure and make it brittle. So the metal is prone to crack and leak. Once leak happens, once hydrogen leaks out of the fuel storage tank, I have several other subsequent problems. One of the problem is the ignition energy requirement of hydrogen is 1/10 of ignition energy requirement for gasoline. 1/10, 1/10. Okay, that is a typical ignition energy required to ignite hydrogen air mixture. Hydrogen air mixture, you know, it has a wider flammability limit or ignitable limit. So it can mix over a wide proportion with the air. Okay, so and ignition energy requirement is 1/10. So any source, ignition source is enough for hydrogen air mixture to catch fire. Once it catches fire, I cannot see the flame. It is an invisible flame. Why flame is invisible? Hydrogen flame is invisible.
Because there's no carbon.
There's no carbon. It's a carbonless fuel. Carbon is what is giving luminosity. Flame luminosity is because of carbon content. Our hydrocarbon fuel like gasoline and diesel are hydrocarbon fuel. So carbon present in the fuel will give that luminosity. You can see it. Hydrogen is a carbonless fuel. So it burns with an invisible flame. This is another problem. I cannot even see whether there is some flame exists near me. Okay, if at all hydrogen catches fire because it's invisible. The other more severe problem is it will move at a very high velocity. Hydrogen flame velocity is much higher compared to the flame velocity of hydrocarbon fuel. Okay, now you can imagine a scenario of storing hydrogen in your vehicle. In case of accidental leak, which is again the probability is very high because of its characteristic. Okay, in terms of lightest gas and its ability to penetrate or diffuse into metallic structure, the tendency for leakage is very high, and the tendency for ignition is very high because its ignition energy requirement is less. I cannot even see. It's invisible and it moves at a high velocity. It means it can do all the damage in no time. It can do all the damage in no time. Okay, this is one of the major threat, right, in terms of safety aspects of this particular fuel. That's why there is a saying about hydrogen. Today we talk lot about using hydrogen in our vehicle, but there is a saying about hydrogen as a fuel. Hydrogen will be the future fuel, will always be. We will never realize hydrogen as the current fuel, primarily because of whatever I said just now. You have all possible worst case scenario of taking hydrogen as a fuel in our vehicle, especially from a safety perspective. Okay, so that's why these fuels are unsafe. I would say gaseous fuels are unsafe and they have a very low volumetric energy density, which is a major problem. Okay, so you have to compress it. There is associated cost and energy involved in compression. So storage and transportation is not easy with gaseous fuel. It's very easy with liquid fuel. You can store under ambient conditions. Okay, and gaseous fuel you have to store at high pressure. So you need to have a high pressure fuel handling, storage, and transportation system to handle gaseous fuel, which is going to be very expensive. Okay, and other when we, you said something?
No, sir.
Okay, so the other important thing with respect to safety aspect is there is a property called flash point temperature. I think you would have come across this. Have you come across this flash point temperature?
Yes, sir.
What is this flash point temperature?
Temperature at which the fuel will just catch
Fire.
Catch fire.
Yeah, momentary flash. It's the minimum temperature at which a fuel can catch momentary flash. Okay, right. It's not continuous. It's a momentary flash. It's a minimum temperature at which the fuel can catch a momentary flash in terms of when we introduce an ignition source. Whenever there is an ignition source available, the temperature, minimum temperature at which the fuel catches momentary flash is flash point temperature. Okay, so any idea about this flash point temperature value for gasoline and diesel? For gasoline, it is minus 45 degrees Celsius.
Diesel
Minus 45 degrees Celsius. For diesel, it is around 60 degrees Celsius. Gasoline, it's negative. Diesel, it's positive. Diesel, it's well above ambient temperature. Our typical Indian tropical climate temperature average temperature is around 30. It's going to increase during summer. It may slightly drop during winter, but it's around 30. Okay, around that. Diesel is having a higher temperature than surrounding ambient temperature. So we are talking about flash point temperature, wherein when an ignition source is introduced, the minimum temperature at which the fuel catches produces a momentary flash is what is flash point temperature. This is quite possible when we go and refuel vehicle, because you open the tank and fuel may mix with air in ignitable range, and whenever there is a source, ignition source available, there is a tendency to catch to form a flash, momentary flash. You don't know what exists around that surrounding. That flash may get transformed into larger damage. We don't know. That's why we need to keep a check on this flash point temperature in terms of storage and transportation of a fuel. So gasoline is negative and diesel is positive. Diesel is well above ambient temperature, so there is no issue. It's a safe fuel. But what will happen with the gasoline? It's a negative temperature. It's highly volatile fuel. I already said about this. That's why when you go and open the fuel tank for refueling, you can feel the smell of gasoline, right? It's a highly volatile fuel.
Yes.
You can feel the smell of fuel when we open the fuel tank. Please note here that some of the hydrocarbon present in gasoline are carcinogenic. What is carcinogenic?
Cancer, cause cancer.
It has a potential. Anything with a benzene ring-like structure has a potential to cause cancer. Okay. So some of the hydrocarbons present in gasoline has a potential to cause cancer. So we should not inhale it. We should not inhale it from that perspective. Okay, so you should keep away from these vapors. this hydrocarbon vapor that evolve out. So the thing we are noting here is it's a negative because it's highly volatile. It can form vapor, but even then it is a safe fuel. So what could be the possible reason?
Because even if it is because even it is volatile, sir, but air is so prevalent in the atmosphere, it is not making the combustion mixture. It's very lean mixture that will make. So probably that is
Diesel, not very lean, very rich. So you will have more vapor in the surrounding. So the proportion of vapor and air will be too rich in the case of gasoline. The proportion of vapor and air will be too lean with diesel because diesel is having higher temperature. Its tendency to form ignitable mixture is very, very less. Whereas for gasoline, it will form too rich mixture. Okay, too rich mixture. So because of that, it is safe. It won't ignite. So here we should note that the fuel air mixture has to be mixed in a finite proportion. Then only ignition can happen. Otherwise, the ignition cannot happen, right? So in the case of gasoline, you will have a too rich mixture. In the case of diesel, you will have a too lean mixture. That's why this fuel during storage and transportation, they won't catch any momentary flash, even in presence of ignition source. So we say that these two fuels are very safe from that aspect. So putting together whatever we have discussed so far, these three characteristics, high volumetric energy density, ease of transport, storage and handling, safe to transport, storage and handling. These three characteristics are the salient features of liquid fuel, which makes them preferable choice for the transport application. As I said, 99% of the fuel requirement in the transport sector is met only with the liquid fuel, and only 1% is with gaseous fuels like LPG and CNG. Okay, so because liquid fuel possesses these three distinct characteristics, especially the fuel produced from crude oil, gasoline and diesel. Okay, gasoline for SI engine application and diesel for CI engine application. So now we have understood the criteria followed to select fuel for automotive applications. So these three are the primary criteria that is being followed. From that perspective, we prefer to use fuels produced from crude oil. So with this understanding, we are moving into the next topic to see the molecular composition and molecular structure of hydrocarbon present in gasoline and diesel, because these fuels we use predominantly for our SI and CI engine. So this fuel, gasoline and diesel, they are obtained from crude oil or petroleum. So we refine crude oil and produce this gasoline and diesel. Okay. So what this refiner is, we don't have crude oil reserve in India. We rather import crude oil. Okay, crude oil from primarily from Gulf countries. So we import crude oil from other countries. We don't have an indigenous crude oil reserve. There is a problem because of this. We want this two fuel, okay, for transport sector. 95% of the demand is met only with this two fuel, and we don't have an indigenous source. The source is crude oil. We don't have that in India. We have very limited reserves, oil reserves. What is that? Could you please mute your mic? Only if you have a query, please unmute. Otherwise, please mute your mic. I'm getting some feedback from you. Thank you. So we don't have this reserve. We have a very limited crude oil reserve. So we import crude oil from other countries. Because of this, you know, there is a problem. Now government, it's out of control of government. Government has given it to the refineries. Refineries can fix the fuel price, gasoline and diesel price. So it can vary every day. This is what we are seeing, right? The price fluctuates because based on the price of the crude oil, the price of gasoline and diesel can be fixed by the refineries. So every day it can change. That is the current status. It is a story status that we have in India because we don't have a indigenous reserve. The price of crude oil is not fixed by us. It's fixed by someone else from where we import. Okay, based on that, the price of gasoline and diesel is going to be different. Okay, so there's a kind of fluctuating price for this two fuel. Even then, we prefer to use only this two fuel for our transport sector. Okay, it's a kind of fluctuation in the price affects economic status also, right? But we don't have an option. You don't have any other option except to go with this two fuel currently. Okay. So we have a lot of refineries, as you know. The largest private refinery is Reliance SR are the private run refineries. We also have government run refineries, right? Bharat Petroleum, Hindustan, and so on. So we have a lot of government and private run refineries, and we have very limited crude oil reserve. We generally import from other countries. So these refineries, what they do, they refine crude oil and produce gasoline and diesel. The processes undergone by the crude oil are primarily done by the refineries to modify the size, molecular composition, and molecular structure of hydrocarbon. Also, they remove the contaminants from the crude oil so as to get into gasoline and diesel. So refineries, they carry out this refinery processes primarily done to modify size, composition, molecular structure of hydrocarbon. We need to get fuel with the required quality. Like emission standard, you have fuel standards also available across different countries. In India, we have our own fuel standard. Any fuel cannot be legally sold in the market unless otherwise the fuel complies with the current standard. Like BS6 emission norm, we also have a BS6 fuel. So the fuel that is sold in the market, in the pumping station, should comply with that current fuel standard. Okay. So there is a legal certification agency that is taking care of. So the refineries will refine crude oil, produce fuel with the required fuel standard, current standard, it should comply, right? So they do all these processes to ensure that the fuel is produced with the required fuel quality. Now let us quickly look at the processes that are done in the refineries. So as I said, the crude oil is taken to the refineries. The refineries, carry out various processes, refinery processes to produce gasoline, diesel, and jet fuel. This jet fuel is also called kerosene or high-speed diesel. Where do we use this kerosene or high-speed diesel? Gasoline is used in spark-ignited engines. This is used in compression-ignited engine. Where do we use jet fuel?
Aviation, sir.
External combustion engine.
Aviation industry, external combustion, gas turbine. So aircraft are primarily, IC engines have very limited application in aircraft, very limited. Okay, small air carriers. Okay, personal air carriers maybe IC engine, but large commercial aircrafts are gas turbine powered, and they are fueled with kerosene. Kerosene, they are also referred to as jet fuel or high-speed diesel. Kerosene. This is a fuel that we use in aircraft engines. Okay, so our focus is only on these two fuel that we. Yes.
Sir, one question, sir. Sir, kerosene, is it the?
Your voice breaks. What is your question?
Is it the same kerosene we?
Hello? Hello? I could not hear you.
Sir, maybe the question is it the same kerosene which we used to have in domestic applications?
No, it depends on the application. For aircraft, for aviation industry, there are certain fuel regulation standard. It may be, the quality may be slightly different. For aviation industry, for IC engine application, there is a fuel specification standard. Similarly, for aviation industry, there is a fuel specification standard. So we need to ensure that it complies with that standard. For kerosene that is used for other application, the specifications are slightly different. Although we refer it with the same name, similar name.
Okay, sir. Thank you.
There are stringent, because these are commercial carriers, right? There are stringent fuel quality requirement that needs to be met. Otherwise, they cannot be legally sold. Right, the kerosene that you get from a local market may be adulterated. There is no stringent fuel quality that is being met. Okay.
Understood, sir. Understood, sir.
Is it clear?
Yes, sir.
Okay, so we do refinery processes. I have highlighted here the 5 important refinery processes that are being carried out in a typical refinery plant, or you will show a layout of a typical refinery plant, Reliance or SR or whatever government run refineries. This is a typical layout of a refinery plant. We take crude oil. We take crude oil as an input, okay, and what we get as an output, here we have gasoline. This is jet fuel used in aircraft engine. Then we have diesel. This is used in SI engine. This is in CI. This is in aircraft. So we get these three fuels. Our focus is only on this two. We are not going to discuss about jet fuel here. But all these three are produced from the same source. Crude oil is a source, and we are refining crude oil to get this three fuel in our refineries. Okay, and we have several processes that are happening in between, right, to get into this gasoline and diesel that we use in SI and CI engine. Crude oil is subjected to these various processes. So the first process that will be done is distillation. I think you will have some idea about this distillation process. This distillation process is done to separate hydrocarbon based on boiling range. This crude oil is a complex mixture, multi-component mixture of hydrocarbon. Different hydrocarbon present in crude oil have different boiling range. To take advantage of differences in the boiling range, we subject them to a distillation process in a column called distillation, fractional distillation column. You have to heat the crude oil in the column, distillation column. Once you heat it, different hydrocarbons evolve out of the column at different temperature range. So primarily we have three distillate that you get from the distillation column. One is light distillate, which is what is gasoline. It has a boiling range of 20 degrees Celsius to 200 degrees Celsius. We use the word light to indicate that it's a low molecular weight hydrocarbon with a low boiling temperature. It is not one temperature, it is a range because it's a mixture of hydrocarbon with the different boiling temperatures. So you have light distillate, which is gasoline, that comes out in this temperature range, 20 to 200 degrees Celsius. Middle distillate is called kerosene or jet fuel. Then heavy distillate is referred to as diesel. Between kerosene and diesel, only the final boiling temperature is different. For kerosene, it is 160 degree to 360 degrees Celsius. That's a boiling range. For diesel, it is 160 degrees Celsius to 380 degrees Celsius, slightly high. The final boiling temperature is slightly high. That's why you use the word heavy distillate. The term light, middle, or heavy is primarily to indicate the molecular weight of the hydrocarbon. When molecular weight is more, the boiling point is also high. As simple as that. So light distillate means you have a lighter molecular weight hydrocarbon that are present in gasoline. Heavy distillate means you have heavier molecular weight hydrocarbon that are present in diesel. That's why the boiling range is high. So for gasoline, it is 20 to 200 degrees Celsius. We are not going to discuss about kerosene, which is used in aircraft. Okay, and then for diesel, it is in the range of 160 degrees Celsius to 380 degrees Celsius. So you see initial temperature, boiling temperature itself is very high. Whereas for gasoline, it's well below the ambient temperature. Ambient temperature, as I said, typically it's 30. Here you have 20 degrees Celsius. So you have gasoline classified as light distillate because it includes lighter molecular weight hydrocarbon with a lower boiling range. Diesel as a heavy distillate because it includes heavier molecular weight hydrocarbon with a higher temperature range. 160 to 380 is the temperature range. Above 380 degrees Celsius, if you carry out the distillation process, the hydrocarbons are going to crack. It won't boil, rather it will crack. That's why they are classified as residue, which comes out as high as 60%. This residue, whatever comes out of the atmospheric distillation column, is also called as tar. Have you come across this term tar? Where do you see this?
Sir, road construction.
Yeah, for paving roads. This is being used for paving roads. It's a thick black liquids You would have seen, most of you would have seen this thick black liquid. This is what is that residue, thick black liquid that comes out of the distillation column. Is tar. It's being used for paving road, but we cannot use only for that purpose. So we have to subject it to further processing. 2% is dissolved gases. In crude oil, you have only 2% of dissolved gases, which is nothing but LPG, which we use for domestic cooking. There is again a huge demand for LPG for cooking purpose. It's only 2% of crude oil. It is present in the form of dissolved gases. As I said, LPG include propane and butane, which exist in gas phase under ambient condition. Okay, it's a dissolved gas present in the crude oil, and that's also being processed, right, in a typical refinery. So as I said, we have around 60% of the residue that is coming out as a thick black liquid. We cannot afford to use it only for paving road. It's going to be very expensive, right? What they do is they will subject it to vacuum distillation. This is carried out under ambient pressure condition. This is carried out under subatmospheric pressure. That is what is vacuum distillation. So in the subatmospheric pressure, the volatility is improved. The pressure is reduced. So the boiling point is accordingly reduced. So you separate hydrocarbon in vacuum distillation at a subatmospheric pressure. Then you take it to various processes as indicated here. I'll give a quick summary of the processes that are happening here. So these are the processes. Just now we discussed about fractional distillation. We are actually separating hydrocarbons based on differences in the boiling range. That's the first step in the refinery process. Then we subject it to various processes. One of the important processes is cracking, thermal and catalytic cracking. This is being done to convert heavier hydrocarbon into lighter hydrocarbon. Heavier hydrocarbon into lighter hydrocarbon. That is what is cracking. This is done by adding heat. The temperature range is very high, around 480 to 550 degrees Celsius. That's a typical temperature range. Thermal cracking is done without any catalyst. Catalytic cracking is done with the catalyst. We are adding heat, break heavier hydrocarbon into lighter hydrocarbon. Okay, that is what is being done here. It is done by supplying heat. Right, you have a high temperature range. In a catalytic cracking, we typically use zeolite as a catalyst, one of the most widely used catalysts for catalytic cracking. So we are converting heavier hydrocarbon into lighter hydrocarbon. What will also happen because of the cracking process is we will end up in producing very small or lighter hydrocarbon which exists in the gas phase. We don't want that for IC application. That's why this process is carried out, polymerization. It's a reverse process of what we have discussed just now. In a polymerization, lighter gaseous hydrocarbons are combined to form heavier liquid hydrocarbon because we want liquid fuel. So for example, C3 level hydrocarbons are combined. C3 is propane which exists in the gas phase. So this will be combined to get C9, which is a heavier hydrocarbon, which will exist in the liquid phase. This is what I mean polymerization process. So you are combining lighter gaseous hydrocarbon to get heavier liquid hydrocarbon. And this is again done at higher temperature as well as higher pressure in presence of catalyst. Then you have catalytic reforming. Catalytic reforming is done to modify molecular structure of hydrocarbon. Later on, I will discuss about molecular structure of hydrocarbon. This is again important to know from combustion perspective. Based on variation in the molecular structure of hydrocarbon, the properties like ignition quality is going to be significantly different. So we need to have an understanding about the molecular structure of hydrocarbon present in gasoline and diesel. This process is done to modify the molecular structure, primarily to increase octane number. To increase octane number, molecular structure is modified through this catalytic reforming process. This is again done at a very high temperature in presence of a catalyst. Catalyst used is platinum. Temperature is around 500 degree plus. So at high temperature, the hydrocarbons are made to react with hydrogen in order to modify the molecular structure. What kind of molecular structure I will show in the subsequent slide. In the subsequent discussion, I will show typical molecular structure of hydrocarbon. But take a note that this is done to improve the antenna quality of the fuel. The last one is hydrotreatment process. Hydrotreatment process is done to remove contaminants from the fuel. Contaminant from the fuel by reacting with hydrogen. The major contaminants present in crude oil are, one is nitrogen, other one is sulfur. So today we talk about ultra low sulfur fuel, right? In BS6 fuel specification, sulfur is also regulated. We talk about a few ppm of sulfur. That's why it is ultra low sulfur fuel. Nitrogen and sulfur are contaminant. They need to be removed by reacting with hydrogen. When you react nitrogen with hydrogen, you will get into ammonia, which is removed. And sulfur, when you make it to react with hydrogen, it forms hydrogen sulfide, which is removed. So that is how we remove nitrogen and sulfur from crude oil, by reacting with hydrogen. We don't want nitrogen and sulfur to present in the fuel, both in gasoline as well as in diesel. So we do this hydro treatment process to get rid of nitrogen and sulfur in the fuel. Okay, this is a kind of purification step in the refinery. So these processes are what these processes are happening here in this region, right? And thereby you get diesel and gasoline with the required fuel specification. This is what our refineries are doing, okay, to get gasoline and diesel with the required fuel specifications. I'll stop here. It's time up. If you have any questions, you can ask. Are there any questions based on the discussion we have today?
Professor, you told that since hydrogen is carbonless fuel, so luminosity of the hydrogen gas is not there, hence we cannot detect the flame, right, sir?
Yeah, yes.
Sir, I'm just a stupid thing that I'm asking you, sir. Sorry for that. Can't we add some some impurity to that, like hydrogen fuel, whether we can detect the flame in that way, like some addition of some radicals or whatever you suggest in that way, which can show that hydrogen is getting the fire?
No, rather than adding some additive to identify the flame, what is generally done is we have this hydrogen detectors. Whenever you use hydrogen as a fuel, there are detectors available which can sense whether there is any leakage in hydrogen. It's relatively less expensive compared to detecting flame. Flame is something which is more dangerous. You should avoid formation of flame. So it means you need to detect the leakage of hydrogen itself rather than detecting the flame.
Sir, stand this question, sir. Just one thing more I want to ask you, sir. Suppose there are many vehicles running on the road. I think Reliance is running some vehicles on the road with the hydrogen fuel, and same is I think some hydrogen fueled vehicle on the road as a proto stage.
Yeah.
So, typically, like you told, so it's like a bomb which is running on the road in that sense.
Yeah.
So, to avoid the explosion, sir, what are the active measures they take actually? Suppose what I mean to say is कि गाड़ी चल रही है and suddenly some accidents happens where the crack can happen and it can lead to flames or explosion. So to tackle those type of scenario, what are the preventive measures which has been
already several guidelines are in place, right? So considering the safety threat of hydrogen as a fuel, already there are several safety measures are in place. For example, if you have to design a storage container for hydrogen, already there are well-laid procedures. So you have to follow it, that's it. But what I mean to convey here is, and you have to take a note here, that there is a very high factor of safety you have to give. It means there is associated cost. Even with all this, there is an element of risk. That is what I am highlighting here. People know the risk involved and they have formulated guidelines with a very high factor of safety. That is how some of the cars or whatever vehicles you said, it's running on road. They are running with very high factor of safety. There is associated cost involved. But what I want to convey here is there is an element of risk.
So thank you so much, sir. Thank you so much.
Yeah. Okay, fine. Anything else? Okay, so if there are no questions, yeah.
Sir, one question, sir. quick question.
Sure.
Sir, like safety and means storage was the major problem with LPG and CNG. So why there is an emphasis on hydrogen fuel when we already see these problems with liquid means gaseous fuels?
Obvious answer for this question is hydrogen is a carbonless fuel. Why government promote this, considering even they know the safety risk, but hydrogen is a carbonless fuel, right? That's why they
Sir-
promote more on hydrogen and ammonia. Ammonia is like a hydrogen carrier, and so ammonia and hydrogen are now currently the most talked fuel for ICE application because they are carbonless fuel. LPG is again a hydrocarbon, right? Propane and butane are hydrocarbon. CNG is methane, CS3, again hydrocarbon. Hydrogen is the only fuel I would say apart from ammonia, which is carbonless. So you are actually, the problem is there is a tremendous pressure, political pressure to reduce, cut down the carbon emission. It's going to be coming in the mandate. That's why all the countries are committed to reduce carbon emission, not only from power plant, also from the transport sector.
Understood, sir. Sir, adding to it, sir, like we are trying to encounter global warming. So the thing is like even H2O in vapor stage is a contamination. It is considered as a impurity. So what about that, sir? Like
H2O, one advantage with H2O is it will quickly condense, right? You can remove
Yes.
it. Air
Yes.
has moisture, right? Air is carrying moisture. Only cooking with H2O compared to other contaminant is it can be condensed based on the prevailing pressure temperature conditions.
Understood, sir.
Thank you, sir.
Fine. Okay,
Thank you
so
so
I'll
much.
stop here. I'll meet you on Monday. Thank you.
Thank you, sir.
Thank you, sir.
Thank you so much.
Thanks a lot, sir.
Thank you, sir.
Thank you, sir.
Yeah, thank you.
அவங்களோட சார்ஜ்